Have you ever wondered how your computer manages to run multiple applications at the same time? Well, the magic behind this seemingly complex operation lies in something called process control. At the heart of your computer's operating system, process control manages and coordinates the execution of programs known as processes. Imagine processes as individual players in a grand orchestra, each playing their parts in harmony to create a beautiful symphony. Just like a conductor who directs the orchestra, ensuring each player starts and stops at the right time, the operating system controls the processes, making sure each one has the necessary resources and instructions to perform its task. From creating new processes to deciding when and which process should run, from terminating processes to managing their states, the operating system does it all. It even facilitates communication between different processes and maintains synchronization to prevent any chaotic situations. So let's dive into the key aspects of process control in an operating system. First off, we have process creation. It's like giving birth to a new task. In the world of operating systems, this responsibility falls squarely on the shoulders of our trusty companion, the operating system itself. It's the operating system that creates new processes, allocating the resources needed for the task at hand. This might involve setting aside memory, assigning CPU time, or initializing data structures. Just like a baker kneading dough into loaves, the operating system shapes these resources into a new process. And how does it do this? Well, if we're in a Unix-like system, the fork mechanism leaps into action, splitting off a new process from the parent. In the world of Windows, it's create process that does the heavy lifting. So you see, the operating system is the master puppeteer, pulling the strings behind the scenes, allocating resources, initializing structures, and invoking mechanisms. Thus, the operating system breathes life into a new process. Next up is process scheduling, the conductor of our symphony of tasks. Just as a maestro directs an orchestra, deciding who plays what and when, the operating system orchestrates the execution of processes. It's the operating system's job to decide which processes to run and when to run them on the central processing unit, or CPU. Picture this: a waiting room full of processes, each anticipating their turn for execution. This is what we call the ready queue. The operating system, acting as the gatekeeper, selects processes from this queue and allocates them CPU time. This selection isn't random, but rather it's based on a set of rules known as a scheduling algorithm. Scheduling algorithms are the secret sauce to process scheduling. They range in complexity and efficiency, each with their unique strengths and objectives. Some algorithms focus on maximizing throughput, ensuring that the maximum number of tasks are completed in the least amount of time. Others might prioritize minimizing response time, striving to start executing tasks as quickly as possible after they enter the ready queue. Yet some algorithms aim to ensure fairness, giving each process an equal share of the CPU time. Choosing the right scheduling algorithm is like choosing the right tool for a job. For instance, an algorithm that maximizes throughput might be excellent for batch processing tasks, where we care more about the total time taken to complete all tasks. On the other hand, an algorithm that minimizes response time might be more suitable for interactive tasks, where quick reaction to user input is critical. So you see, the operating system, through process scheduling, ensures that all processes get their fair share of CPU time. It balances the needs of the tasks, the objectives of the system, and the constraints of the hardware to create a harmonious performance of all tasks. It's a delicate dance of prioritizing, queuing, and allocating, all orchestrated by the operating system. This way, the operating system ensures a harmonious performance of all tasks. And that, my friends, is the art and science of process scheduling. Every process has an end. It's called process termination. Just like a player bows out after a captivating performance, a process too ceases to exist when its job is done. This can happen voluntarily, for instance, when a process completes its task and calls it a day by invoking functions like exit in C language. On the flip side, a process could also be shown the exit door involuntarily, say, due to an error or an external signal. But what happens after the curtain call? The operating system steps in, playing the role of a diligent stage manager. It takes charge of cleaning up, releasing resources that the process had occupied. Memory, CPU time, I/O devices, you name it. The operating system also takes the responsibility of notifying any relevant parties, like the parent process, about this termination. Thus, a process gracefully exits the stage when its role is done. Processes live a dynamic life. They change states and communicate with each other. In the realm of operating systems, a process can exist in a variety of states. When it's actively executing instructions, we say it's in the running state. But processes don't always get to run continuously. Sometimes they enter a ready state, patiently waiting their turn to use the CPU. At other times, they might be blocked, waiting for an event like the completion of an input-output operation. Then there's the terminated state, which is the end of the road for a process. The operating system plays a key role in managing these state transitions, ensuring that processes move smoothly from one state to another based on events and conditions. But processes aren't isolated entities. They often need to communicate with each other, perhaps to synchronize their actions, share data, or coordinate tasks. This is where inter-process communication, or IPC, comes into play. IPC is a set of methods that processes use to exchange data. For instance, message passing allows processes to send and receive messages from each other, while shared memory lets multiple processes access the same section of memory. Then there are pipes and sockets, which provide a pathway for data between processes, and semaphores, which are used to control access to shared resources. These communication mechanisms are crucial because they enable processes to work together in harmony. Imagine a symphony orchestra where each musician plays a different instrument. Without proper communication and coordination, the result would be a cacophony rather than a harmonious melody. Similarly, in the world of processes, IPC mechanisms ensure that all processes work together in a coordinated manner, each doing its part at the right time. So, whether it's transitioning from one state to another or communicating with fellow processes, every process has a dynamic journey in its lifetime. And it's the operating system that orchestrates this journey, ensuring that everything runs smoothly. These mechanisms ensure smooth interaction and prevent chaos in the world of processes. Processes need to play nice with each other. That's where synchronization, suspension, resumption, and prioritization come in. When multiple processes access shared resources concurrently, there's a need for synchronization. This is to prevent what we call race conditions and to ensure data consistency. Imagine two processes trying to access and modify the same piece of data simultaneously. It can lead to unexpected and undesirable outcomes. So, operating systems offer synchronization primitives like locks, mutexes, and semaphores to coordinate access to shared resources. It's like having a traffic warden at a busy intersection, ensuring that cars don't collide. Now let's talk about process suspension and resumption. Sometimes, operating systems need to temporarily suspend processes. This is usually to free up resources or to prioritize other tasks. It's akin to pressing the pause button on your music player to take a phone call. The music is suspended, but it doesn't lose its place. Similarly, processes can be suspended and later resumed without losing their state. The operating system keeps track of all the necessary details so that the process can pick up where it left off. And then we have process prioritization. Just as in real life, not all processes are created equal. Some are more important than others. The priority of a process can depend on a variety of factors. These can range from user importance, system requirements, to real-time constraints. For example, a process handling user input or system-critical tasks may have a higher priority than a background task. Operating systems support mechanisms for setting and adjusting process priorities. It's a bit like a VIP pass at a concert, allowing certain processes to jump the queue. So, it's all about balance and harmony in the world of processes. The operating system acts as a master conductor, orchestrating the performance of multiple processes, ensuring they work together smoothly and efficiently. So, in summary, process control in operating systems is a fascinating world. We've journeyed through the creation of processes, where the operating system allocates necessary resources and initializes data structures. We've seen how process scheduling decides which processes to run and when, optimizing efficiency and fairness. We've uncovered the mystery of process termination and how the operating system tidies up, releasing resources and notifying relevant parties. We've delved into the different states a process can exist in and the vital role of inter-process communication in synchronization, data sharing, and coordination. We've also explored how operating systems synchronize multiple processes accessing shared resources and the mechanisms to suspend, resume, and prioritize processes. All these aspects of process control are crucial for the efficient and reliable execution of multiple tasks concurrently. Next time you open multiple applications on your computer, remember the intricate ballet of process control happening behind the scenes.